Thank you. I'll begin with a word of prayer. Dearly Father, we thank you for this day. Again, Lord, I thank you for these students. I just pray you'd just bless our work today. Help us to just understand a little bit more about power series. Lord, in your name I pray. Amen. Yes, it is true. And I'm very happy that some of you are reading ahead. That's fantastic. That's like a good idea. But I'm actually going to talk about, what is a power series, because I think we should talk about that just formally before we talk about how to connect this with functions which are given by other means. So I'm going to talk about what is a power series and try to settle that to start with. So basically, definition. If f of x is equal to the sum n equals to 0 to infinity of a sub n times x minus, let's say, x sub naught to the n, right? Now I can expand on that. That would be like a naught plus a1 times x minus x naught plus a sub 2 times x minus x naught squared plus dot 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 dot. Then f of x is a power series centered at x naught with coefficients a sub naught, a sub 1, a sub 2, and so forth. So just to be clear, we assume these are real numbers. So there's like a natural correspondence between a given power series and its set of coefficients. If you give me the set of coefficients for the power series and you give me its center, then you've defined the power series. All right? So like in words, what's a power series? I could put it in words here. So a power series is a function whose formula is given by a series at each point in its domain. Now that's not entirely honest, because in principle you could imagine a function where you give a different coefficiented series at different points, right? It's a little bit more than that. It's not just that it's a series at each point in its domain. It's that it's this same. These series are related. They all have the same coefficient. All right. So, but more. I mean, this is the definition right there. Power series is a function which point-wise has a formula like that. All right. So can you tell me what point is always in the domain? So what's the domain of a power series look like? What's it look like? What's one point you can tell me is always? So let's continue to refer to the one in the definition. Oh well, I tried. How about this? And let me continue to work with that same f. So if f of x is equal to the sum, right, n equals 0 to infinity of a sub n x minus x naught to the n, then what's f of x naught? What happens when you set x equal to x naught? Yeah. I'm sorry? Yeah, this is x naught minus x naught, which is 0, right? So 0 to the n is just 0. So this is the 0 series, which is converging to 0. So in other words, yeah. I guess one of the things I should say is what's the maybe what should the domain of the
The first term over there isn't 0 to 0 indeterminate.
Well, this is not something limiting to 0. This is 0.
So the indeterminate forms implies for
I mean, you could show that the nth partial sum for x is just equal to 0. You know, for any n. I mean x naught. Sorry.
Okay, so in this context, we assume that 0 to 0 is 0.
Well, there is no, well, yeah, I mean, well, I think we take 0 to the 0 to be 1. I mean, I think we take 0 to the 0 to be 1 here, to be picky. Take it to be 0. It doesn't matter.
Yeah. Okay.
Well, I guess it does matter. I want it to be. You know what? You're right. Actually, that does matter. That matters a lot. What is this? I'm sorry. You're exactly. Thank you. That's actually very helpful to me because I was about to get really, really confused. But you're right. This should not be 0. This is what? Well, it should actually be a sub naught. See, because if you think about f of to be more explicit, this is a naught, right? Plus a1 times x naught minus x naught plus a2 times x naught minus x naught squared plus da da da, right? Yeah, so I should be careful. My notation almost trapped me. So these are just 0. This is the 0 series.
Okay.
But the first term remains, which is just a sub naught. Yeah. Any questions? So what's the domain? The domain of f of x, all right, is called the interval of convergence. The interval of convergence, which we'll also abbreviate by IOC because, well, that's less writing. And of course, that kind of makes you go, that kind of puts the cart before the horse a little bit. Like, how do I know that the domain of a power series is going to look like that? All right. But there's a theorem, and the theorem says this. If, f of x is equal to the sum n equals 0 to infinity a sub n x minus x naught to the n, then then the domain of f of x is one of the following. So one case, it could just be that your power series has domain, which there's one point which is always included, right? Because a naught's just a number, right? So it could just be that it's just the singleton. It's just the set containing the one point, the center of the series. There's always at least one point in the domain of a series, a power series, provided that the coefficients, a sub n are well defined. So that's one case. The other case is you could have that the domain of f of x, and I'll illustrate all these cases in just a second here, guys. It could be that the domain is the whole deal. It could be the whole real line. That's what that symbol means. That's the real numbers. That's another possibility. It could be that the series, the power series, makes sense. It converges for any x. But the third case is actually 4 cases. The third case, though, is that the domain of f of x is either equal to x naught minus r, comma x naught plus r, or closed interval x naught minus r, x naught plus r, or it's x naught minus r, x naught plus r included, or it's x naught minus r, x naught plus r not included. So every set I've written here, I wrote here for the domain of the function, these are connected subsets of real numbers, meaning that if I was to draw the graph of these domains on the number line, you could do it without picking up your pencil, pen, crayon, whatever floats your boat. And so these are all intervals. They're connected subsets of real numbers. And in every one of these, we can define, these are the intervals of convergence that are possible. And each one of these has a well-defined what's called radius of convergence. So what's the radius of convergence for case 1? 1. Nope, not 1. Nope. This case 1, the radius of convergence, which we'll call r, is just 0, right? What's the radius of convergence in case 2? I'm actually making a definition here. The radius of convergence, the ROC, is in fact infinity for case 2. And the radius of convergence in case 3, it's the r that I put here, right? So r is the radius of convergence. So the standard introductory question we ask is, given a power series, find its interval of convergence. All right? So let's look at some examples of that, and we'll see these different cases arising. All right? So now, I can also talk about the open interval of convergence. The open interval of convergence is the largest open set on which the power series converges. So like, in this, if we're in case 3, for every one of these, the open interval of convergence is just the first thing I wrote. This is the so-called open interval of convergence. Anyway, if I ask you to find the open interval of convergence, I'm being friendly. That means you don't have to check on the endpoints. But if I just say find the interval of convergence, then you got to worry about what happens to the endpoints. Those are the possibilities. So let's look at an example. This one won't have endpoints, though. This one will be rather silly. So here we go. F of x equals to the sum n equals to 0 to infinity of, let's say, n factorial times x minus 2 to the n. So how would we decide which x, how would we decide whether or not this is a convergent series? What tool should we use? Nth term test, integral test, root test? The answer is almost always ratio test for these. So we use ratio test. So let's say n factorial, n plus 1 factorial times x minus 2 to the n plus 1 divided by n factorial times x minus 2 to the n, right? What is that? That's equal to n plus 1, right? Times what? Well, times x minus 2. And so what's the deal with that? Can you guys tell me what happens with that? What happens as n goes to infinity to the ratio of the terms in the series? So it goes to infinity for x not equal to 2, right? As n goes to infinity. Well, let me write that as n goes to infinity for x not equal to 2. So if you take the power series, right, and you fix x, what do you have? When you fix x, you're left with a numerical series, which we just talked about yesterday, right? Talked, maybe is the wrong word. You suffered through yesterday. And so the point is, therefore, f of x diverges, right, for x not equal to 2. Therefore, the interval of convergence here, in other words, the domain of f of x, is just the set containing 2. So there's a case 1 example for you. All right? Yeah.
So 0 times infinity then, I assume, isn't indeterminate. It is determinate 0 times infinity.
Right. If x is equal to 2, this is not n plus 1. This is 0.
Okay. Because that goes to 0 before we apply the limiting process.
Yes. Yeah. It's the limit of the 0 sequence. So yeah. This is, again, I'm using. I should really say that by a ratio test. Okay. Example 2. What if we have f of x equals to, say, the sum n equals, I don't know, 1 to infinity of n times x minus 1 to the n over, oh, I'm sorry, there's no n upstairs. Let's say n squared, n downstairs. There, that's a good one. N equals 1 to infinity of sum n equals 1 to infinity of x to the x minus 1 divided by n. So this has, what are the, so, we can look at x minus 1 to the n plus 1, right, divided by n plus 1, divided by x minus 1 to the n, divided by n. That's my ratio. Let's clean that up a bit. So it's really x minus 1, right? X minus 1 times n over n plus 1, right? What's the limit of that for fixed x? Fix x and let n go to infinity. Here, it's helpful for me to write this. I should really write this for you guys. I've gotten lazy in my formatting, but well, before we get to that, x minus x is fixed here. In other words, it has no n dependence, all right? So it's a constant with respect to this limit in n, which means we can pull x minus 1 out of the limit, right? And then you said L'Hopital's. I mean, we could do that, but at this stage in the game, I'm completely fine with you guys just going, that is a simple limit. We know that that goes to 1. But yeah, you could L'Hopital it. You could do algebra 1 over.
I thought infinity over infinity was indeterminate.
It is, but here, 1 over 1 plus 1 over n, right?
Oh, sorry.
But yeah, you could do L'Hopital's rule too. That's fine. I'm not disagreeing with you.
No, that's, yeah.
But to be more careful, what does the ratio test say we actually look at? Does it say we look at an plus 1 over an? Now that terminology is a little bit dangerous. See, because I used a sub n over here, not for the whole thing forming the nth term in the series, but for the coefficient of the x minus x naught, right? So really this whole thing is what I would have called a sub n before, right, for fixed x. So there's a slight danger there conceptually. But anyway, so if I call this, let me call this thing b sub n just for the sake of being confusing. So if we look at the absolute value of bn plus 1 over bn, we have just worked out that the limit of this as n goes to infinity is what? If you follow through the absolute values, you get x minus 1, right? So what does ratio test tell us? If that is less than 1, this series converges absolutely, right? So we got to take that apart. What does this mean? That means minus 1 less than x minus 1 less than 1, right? In other words, 0 less than x less than 2. So what I've done so far, so in other words, I have that the 0, comma 2 is a subset of the interval of convergence. I mean, I can tell you for sure that the radius of convergence here is 1. And the center of the series is 1. Everything's 1 here, goodness. But the question then is, what about the endpoints? What about f of 0? What about f of 2? Those the ratio test is inconclusive for, right? Because f of 0 and f of 2 give you an absolute value of 1 for the ratio test. All right, so those we have to check endpoints. So those require separate arguments, to be careful. So what is f of 0? Go back to here, plug it in, what do you got? Looks like minus 1 to the n over n, right? Right, that's the alternating harmonic series. We know that this converges by previous discussion, right? It's a alternating series test, right? And f of 2, what is f of 2? F of 2, well, that's the, what is that? And she's loud. Let's see here. Minus 1 to the n, x, f of 2 is what? Oh, that's 1 to the n, right? What's 1 to the n? Just 1. So f of 2 is the p equals, this is p equals 1. It's divergent, right? So the endpoints, I cannot pick up on what's happening at the endpoints with the ratio test. I have to consult other methods, right? So what's the interval of convergence then? Put this all together, what's the answer? So it looks like 0 is included, right? But 2 is excluded, and there you go. That's how you find the domain of a power series. Well, it's one way. We find the interval of convergence by the ratio test, and then check endpoints. Now, when you check endpoints, it could be any of our previous methods. It could be nth term test. It could be, who knows what it's going to be. It could be a lot of different things. Can you guys see how I could modify this example ever so slightly and make the interval of convergence include both endpoints, what would I do? How could I change this example ever so slightly and get the interval of convergence to be 0 to 2 inclusive? How about this? What if I just put a 2 here? If I put that 2 there, this will make the interval of convergence equals to 0 to 2, right? Because the ratio test would work out pretty much the same, right? Instead of having, you'd end up with like n squared, and it would be this. This still limits to 1. You're still left with an absolute value of x minus 1. So you still get the same open interval of convergence. And then when you check endpoints, you see what you got. You've got the alternating p equals 2 series and the p equals 2 series, which would converge. So this is an example where both endpoints are included, and yet it's a finite interval of convergence. Make sense? Let's see here. How about, we still haven't seen case 2. Can you guys, what do you think would be a good example of case 2? How about this? What if we have f of x equals to the sum n equals 0 to infinity of, let's say, 2 to the n times x minus 3 to the n over n factorial? So this is a power series centered at 3, right? And we can try to find its interval of convergence. Now, I say that usually we have to check endpoints. Ratio test doesn't give us everything, but this one's going to be different. Check it out. So if we look at the absolute value of 2 to the n plus 1 times x minus 3 to the n plus 1 divided by n plus 1 factorial, right, times n factorial divided by 2 to the n times x minus 3 to the n. So I'm thinking ratio test. All right. Ratio test. Then how does that work? How does that simplify? So we say it's 2 times x minus 3. So this reduces to x minus 3. That reduces to 2. And, oh, we're left, oh, look, check that out. We're left over, an n plus 1's left over. Woohoo. So if I look at the limit as n goes to infinity of, the absolute value of b sub n plus 1 over b sub n, just to give it a name, calling these things b sub n, then that works out to the limit as n goes to infinity of what? Of 2 times the absolute value of x minus 3 over n plus 1 is constant, so it's positive. I can pull it out of the absolute value. But, what goes on here is that's 2 times the absolute value of x minus 3 times the limit as n goes to infinity of 1 over n plus 1. Yeah? What? No?
You said n plus 1 is constant?
Not constant. N plus 1 is positive, so I can pull the absolute. I don't need to keep it inside the absolute value, is what I was trying to say. I failed. But anyway, again, that same idea, x is no dependence on n, so I can pull it out of the limit. So what are you looking at? You're looking at limit as n goes to infinity of 1 over n plus 1. What's that do? It's 0, yeah. So this is 0. So this is 0 with no condition on x, right? So what's that mean? That means that the ratio test says that this series converges for any x. which I will try to squeeze in here. Thus, this series f of x converges for each x in the reals. So the interval of convergence here is the whole real line. Yes? No? Oh, okay. Check. Now, is there any way out of this? Is it just always going to be ratio test, ratio test, ratio test, ratio test? Is there any escape of the ratio test? Well, I mean, it depends on the example, of course, but there is another way out. I'll show you that. So sorry if this lecture is kind of boring. I mean, all I'm doing today is for the most part, just talking about how do you understand the domain of power series. But that is the first and, well, really, it's probably the trickiest question that you can ask about these things. Example 4. We could look at f of x equals to 1 minus x squared plus x to the 4th minus x to the 6th power plus dot, 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 dot. So this is an example of what's called a Maclaurin series. Maclaurin series, I can't. Which is just a power series centered at 0. So, all right. But what else is this? I mean, you can rewrite the formula. Yeah?
It's also a Taylor series, isn't it?
Yes, a Taylor, I mean, in fact, well, I guess philosophically, to say something's a Taylor series, I need to be given a function, and then I take derivatives of the function to construct the series, right? So like, to say something's a Taylor series, I need another function, and then I can say it's the Taylor series of a function. So the question is, Taylor series of what? See, this is just a power series, But in about 3 seconds, we'll get what function it is the Taylor series for, so you're not wrong. This is what? This is the summation what? What's the formula here, guys?
X to the n. No, -1 to the n plus 1.
I'll tell you what. Let me make it simple. Let me make these all pluses. How about that? That's better. There we go. Pluses. All pluses all around. Now it's easier. What is it? X to the n. Almost. It's how about x squared?
Oh, sorry. Yes.
X squared to the n, right? So this is a what? No. Yeah, this has the form a r to the n equals 0 to infinity, right? Which is equal to what? A over 1 minus r for the absolute value of r less than 1, right? Geometric series. So this is a geometric series. So what this converges when? This is geometric with a equals to 1 and r equals to x squared. Thus, f of x converges whenever what? The absolute value of x squared is less than 1. But that's the same as aka we just want the absolute value of x to be less than 1. So therefore, the interval of convergence here is equal to -1 to 1. No ratio test. But we could say more. We could actually connect this to a known function, right? Let's see here. F of x equals to what? F of x equals to? Yeah, on the one hand, it's equal to 1 plus x squared plus x to the 4th plus x to the 6th plus dot, 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 dot. But that actually equals to what? By the geometric series result, that's also equal to a over 1 minus r, right? Which is 1 over 1 minus x squared here. So the fact that the interval of convergence is minus 1 to 1 kind of makes sense. If you think about this, and this will be more the subject of future lectures, but it's not bad to start thinking about it now. So we're given this function. You could think about this, you could turn the table here. You could say, I'm given the function, f of x with the formula, the rational function, 1 over 1 minus x squared, you know? And then you could say, what does this power series mean? And so if we look at the graph of 1 over 1 minus x squared, what's that look like? You guys know how to make a graph of that? You draw a sign chart. You got your division by 0 at minus 1 and 1, right? Because 1 minus x squared is 1 minus x times 1 plus x, so it's got zeros at 1 and minus 1. Those are the vertical asymptotes in the graph. And you just need to plug a point in each thing. So if I'm left of minus 1, then this is negative. If I'm between minus 1 and 1, for example, 0, it's positive. And then if I'm past 1, again, it's negative. Asymptotically, it goes to 0, so the graph has to look like this. And let's see, what's it at 0? I plug in 0, it's 1, right? So it has to look something like this. Wait a minute, did I do that wrong? Oh, it's always positive. I got the wrong graph. It looks like this. Right? This doesn't happen because it's positive between minus 1 and 1, right? Can't follow my own sign chart, you know? So what's going on here is we have this approximation of this rational function, right? This guy right here, 1 plus x squared plus x to the 4th plus x to the 6th plus dot, 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 dot. This is a way of approximating 1 over 1 minus x squared. In fact, it's not an approximation if we keep the plus dot, dot, dot. But 1 over 1 minus x squared, that looks like this here, right? And so let's see here. So you can actually sort of look at these systematically one at a time, right? Like if you just keep the first term in the power series, you just have 1, right? So the first Taylor polynomial, are you happy? That's here. Would be this guy. So y equals to 1. And then what's the next thing up is 1 plus x squared, right? 1 plus x squared looks like what? 1 plus x squared looks more like, you know, I don't know what exactly it looks like, but I'm not sure if it's above or below the green line. I really don't know. But anyway, it's something like this. Well, but it doesn't have to, it can cross the vertical asymptotes, right? So there's something like y equals to 1 plus x squared. What happens as you add x to the 4th? What is the deal with x to the 4th? It's more like a football, like the, you know, football. Oh, I'm sorry, I try not to talk about that. What's wrong with me? I remember when Ted Cruz was a candidate and he referred to it not as a basketball hoop, but towards the very end of his campaign, I think he referred to it as a basketball ring. Now, for most people, that was a mark against him, but for me, it made me all the sadder to see him go. Like, how do you get through life, adult life in America, and not know it's a basketball hoop? I don't know. That's wow. Anyway, so if you add x to the fourth, it bends it up even more, right? Oh, that's not that good a contrast. Oh well. And see what happens as you add more and more and more, it gets steeper and steeper and steeper, right? And it eventually approximates this 1 over 1 minus x squared function between the vertical asymptotes, right? Yep.
Is that like, so is that, what about like bigger functions? By like bigger function, like, I mean like spread out across like the x-axis. What if it's not between? Like,
Or what if there aren't vertical asymptotes, right?
yeah. So
Yeah. Great question. Great question. So example 5. Let's turn the tables. Let's look at g of x equals to 1 over 1 plus x squared, right? What's the graph of 1 over 1 plus x squared? This guy, it's 1 at 0, and it's just kind of boring, just kind of like this, you know? It's just not really, it's kind of nondescript. And let's see, so what's the Maclaurin series for this function centered at 0? We can use the geometric series idea to find it again. See, we can look at this backwards. We can say, aha. Aha. A equals to 1, R equals to what? You got to look at it the right way. This is 1 over 1 minus x squared, right? Then it has the right form. It's in the form A over 1 minus R. So I use the geometric series result if I put R equal to minus x squared, right? So this is equal to the sum, n equals 0 to infinity, of minus x squared to the power n. Let me just clean it up a bit. This is equal to the sum, n equals 0 to infinity, of minus 1 to the n, x to the 2n. Or if you like, it's very, very much related to the one we just did. This is 1 minus x squared plus x to the 4th minus x to the 6th plus dot, 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 dot. And when is that power series I just wrote apply? When does it approximate 1 over 1 plus x squared? When is it the so-called Taylor series of G? When is this the Taylor series of G?
when it meets all like the qualifications for it, or like if it only meets the qualifications for it.
We need that the absolute value of R is less than 1, right? Because that was the... We'll prove in a later lecture that it has to be unique. So if I can find it by one method, then the other method will learn to find Taylor series and produce the same thing. Fine. So what's R? R is minus x squared, so it's the same. This is, again, the interval of convergence for this guy is minus 1 to 1, right? So you see your intuition can be misleading. Yeah, this had limitations because it had vertical asymptotes. This doesn't seem to have any kind of limitations. It's smooth everywhere, smooth. Very nice function. But for some reason, we can't get beyond here. If we center the series here, right, that's the interval of convergence. It just gets out to there. And that's why you have to be careful. That's why we need to be, not just work on fuzzy intuition. But this is a deep mystery of calculus. Why is this, that it only works from minus 1 to 1? Do you know why?
Is the derivative, can you take the derivative necessarily and have it not equal? Like, isn't that one of the qualifications of differentiable and non-differentiable?
Oh, this thing is smooth everywhere. The problem is this. If you look at the function 1 over 1 plus z squared in the complex plane, you see there's trouble here and there's trouble here at I and at minus I. If we look at this corresponding function g of z, this has singularities in the complex plane here and here. It turns out in complex analysis, when you prove these things carefully, you'll find out that the domains of convergence for complex series are actual honest-to-goodness disks. And so that disk, when it hits the real axis, is just this to this. But that's something you can really only understand properly from the perspective of complex analysis. It will forever be mysterious if you only study real variables, which is why we shouldn't just study real variables, by the way. But anyway, this comment brought to you by unrealistic DCP expectations of the math department, more specifically me. Oh, I think we're done, so you can hit it. And I have your test.